Hello there. Let's do an introduction to Cloud for Network Plus. Remember, this is an introduction and this is Network Plus, and CompTIA does already have dedicated cloud courses. So let's start out with the basic cloud concepts. First of all, why does everyone get so hung up over cloud computing? What's the big benefits and selling points to it? Well, first of all, massive scalability. Especially if you are using a public cloud service provider, I can guarantee you they have more resources than you can afford to use. So you have effectively got infinite scalability, at least as far as your budget is concerned. Now, as far as that scalability is concerned, we have got the ability to scale horizontally. This means we can have more computing instances in a cloud environment as and when we need to. This isn't too special though, because we can horizontally scale a traditional physical data center just as easily by adding new servers. However, cloud does offer us the ability to vertically scale our systems as well. Instead of adding more servers, I can add more CPU, memory, storage, etc. to my existing virtual servers that we'll be running in the cloud. But besides scalability, cloud also brings to the table elasticity. We have not just the ability to grow as we need to, but we can also decrease our operations in the cloud as well. So when an organization has less need for computing resources, instead of that processing power sitting there doing nothing, you can stop allocating as much to your cloud instances, bringing the performance level down and subsequently the costs as well. Now this means that your cloud operations can be seen as an operational expense where costs go up and down as the computing demand and hopefully the revenue goes up and down as well. Unlike traditional data centers where it's seen as a capital expenditure, where you have to purchase equipment and hope it makes return on investment before the equipment becomes too old, outdated, and incapable of keeping up with modern demands. Adding to that, we also have the ability to deploy very, very quickly. You can go from identifying the need for more computing capability to having that within a matter of hours, minutes, or even seconds, depending on how you set up your cloud system and your automation and orchestration systems. And as I've already alluded to, we also have utility-based billing. One of the interesting advantages is that you are going to be paying as you use cloud resources. So as you use more, you pay more. As you use less, you pay less. And a lot of the cloud providers have moved to a per second billing model, meaning that if you decrease your compute resources right this instance, so will your bill decrease. And we also get some of the benefits of offloading some of our responsibilities, because the cloud provider will become responsible for some aspect of our operations, and we obviously still have some of our own still. But this can help take some burden off of an organization's IT department. And last but not least, something called ubiquitous access, which is just a really cool way of saying that as long as a client or user or even customer has internet connectivity with a device with a browser, they should be able to access cloud resources. There should be no operating system or protocol limitations imposed upon them, at least hypothetically speaking. Security might decide otherwise. So let's talk about some cloud deployment models. First up is public cloud. This is where we normally see all of the big benefits and advantages of cloud computing, as we are going to be paying a big name cloud provider like Microsoft, Amazon, Google, etc. to host our resources. Now, the big advantage here is because you, me, and anybody else using their environment, we are not just using it, but we're also sharing it. So we help to share the costs. It's sort of like if you want to run a transport business. You can go and buy a bus. Very expensive vehicle, but selling tickets to ride on that vehicle will not be too bad because there's plenty of seats, loads of space for people. So that helps to absorb the cost of purchasing and operating such a large and expensive vehicle. And a public cloud data center is no different. However, it does come with a big caveat. You are sharing that space with other customers. Now, what's so bad about that? Well, we are relying on the cloud provider and the technologies they're using, such as virtualization, to help keep the customers separated from one another. Now, before I get too carried away with saying customers, the correct term for a customer in a cloud environment is a tenant. I will probably jump back and forth between those two terms continually while we're in this video. Now, for some organizations, that shared environment is a big issue because it is possibly a security liability and also a privacy liability. In which case, you could look at something called a hosted private solution, sometimes referred to as a single tenant solution. This is where a public cloud service provider can guarantee you will be the only customer or tenant on that server. You will not be sharing it with other customers. Now, this does come at a higher price because obviously they've got to dedicate that physical computer to you, whether you're going to use all of its resources or not. The benefit, though, is you will be able to scale without concern when it comes to, maybe I've run out of space on that server. There probably will be more space. And you also will have better performance as well. So there are going to be some distinctive advantages to this besides the fact that you are the only customer and therefore a bit more secure and private. But if you want full control and certainty over your data and your operations and security, private cloud might be the right option for you. With private cloud, you basically become your own cloud service provider. This is where an organization would essentially use their own data center and use quite a bit of virtualization and other technology to offer that data center's resources to the users as though they are the cloud provider and the users are the consumers. Now, big advantage is you do retain control of everything. The downside is you're retaining control of everything, which means you are also responsible for everything from the hardware upwards. You will also run into challenges when it comes to scaling at some point, but you do get some advantages of being able to borrow resources from one department who's not using them and allocate them to a department who does need those resources right now. So you are going to have more optimal usage of your data center equipment. Then you get a community cloud. Now, community cloud is sort of a semi-private cloud that is operated by the community that uses it. So a bunch of organizations might get together and decide to co-host their own private cloud. This can be quite advantageous as the organizations in question can try to ensure that they're compliant legally and regulatorily, as well as have quite a lot of confidence over the underlying operations that support the cloud service. And then lastly, you get a hybrid cloud, where we mix and match different elements of the above cloud deployment models. Holistically, when you look at most organizations and their cloud deployments, they usually will go hybrid. Some things will be kept private, some things will be kept in the public space, some stuff might even be hosted traditionally and conventionally. Most organizations ultimately land up overall as a hybrid cloud deployment. I don't think I have ever seen any organization be completely 100% private, public, hosted, or anything like that. Now, besides the deployment models that can be used to differentiate cloud services and cloud operations, we also have service models that can be used to distinguish how our cloud operations look. And chances are, if you've looked at this before, you've seen this pyramid, where we have infrastructure as a service, platform as a service, and software as a service. Now, sometimes the pyramid might be the other way around, where the apex is at infrastructure and the base is at software. But I personally prefer the pyramid when it's drawn like this, and you'll see why later. So let's understand what's going on with infrastructure as a service. The short version is the cloud service provider, or CSP, will run the hardware resources, making them available to the consumer, usually through some sort of hypervisor console. The consumer, or customer or tenant, whichever term you prefer, will deploy their operating system, services, applications, and data. Now, it will also be the consumer's responsibility to handle all of the software elements, OS licensing, services, application maintenance, data security, etc. All of that will be in the customer's hands. Effectively, with infrastructure as a service, the organization has offloaded the hardware responsibility of their data center operations. But you know what? We could get a bit more out of this with platform as a service, where the cloud service provider will run hardware, the operating system, and some of the basic services needed to have a computing environment. The consumer will deploy their services, apps, and data. So a bit of the basic software stuff has been handled by the cloud provider, freeing up the consumer to worry about just running what they need to run. and not worrying about making sure the underlying OS and its basic services are working correctly. And then we have software as a service, where the cloud service provider runs the hardware, the operating system, the services, and the apps. And the consumer is effectively paying to access the apps and is responsible for the data and the user access to that environment. Now, the reason why I like the pyramid this way is just like building a pyramid. As you go up, the cost goes up because it does cost money to elevate building material to some height. And yes, the consumer will pay more as the cloud provider is doing more the further you go up this pyramid. But then conversely, if you go further down to the bottom of the pyramid, just like building a pyramid, there's more work to do building the base than the apex. And the consumer has more work to do at infrastructure as a service, as the consumer is responsible for the OS, all the services, the applications, etc. Whereas at software as a service, the consumer's only got to worry about their data and how they manage user access. So that helps out quite a lot. But this pyramid and model worked great 15 years ago. Nowadays, we have way more than just these 3 cloud services. So we've got a couple new members that have joined the party, such as database as a service, where basically your entire database and possibly even its front end and middleware can become a cloud service. You also get communications as a service, where everything like email, instant messaging, collaboration tools, etc. have become a cloud service. The most annoying one for me, network as a service, which is really frustrating because a lot of people think, hang on, how does my network become a cloud service when I need my network to get to the cloud? They should have called it network monitoring as a service, where essentially Network Operations Center and network monitoring can be a cloud service now. You also get security as a service now as well, where a lot of security utilities like encrypted communications and so forth could become a cloud service, and the list keeps going on and on and on. All it takes is somebody to either figure out a way to take a traditional IT service and deliver it as a cloud service, or come up with a brand new IT service and start deploying it and delivering it as a cloud service, and voila, you now have a new cloud service model. Thankfully, the Cloud Council, yes, they do exist, that is the name, created something called XAAS, or Anything as a Service, where pretty much nowadays any computer and IT service could become a cloud service, which is great. Now, as cloud computing has become more pervasive, content delivery networks have also become more pervasive and widespread as well, and not just for things like multimedia streaming, but for all kinds of data delivery, as we are consolidating and storing our data and operations in a very central location, the cloud data center. And users who are quite geographically distant from that data center experience significant latency. And the idea of a content delivery network is we are going to replicate data closer to the users that are using it, so that the requests spend less time traveling to and from the servers and the users get that data quicker. So if we look at a little global map here, for instance, and we have our original server sitting somewhere in North America, but then we're going to have people all over the world that need to access this data. Now, the further away you are from where that server is, the more time it's going to take that data to travel, regardless of how fast the internet connection speeds are, whether you're looking at transatlantic cables or anything within a country. You are looking at more distance, and distance is going to affect the time for travel. So what will happen is we'll deploy servers all over the world in strategic locations, and then replicate data amongst those servers, or data centers even. Now, whether we replicate all of the data or just the data that is very commonly accessed in those regions, that will vary. But nonetheless, though, a CDN server will make it a lot easier for somebody in Europe to more quickly access data that they need to get access to than going all the way across the ocean. And even more so the further away you get. So more and more cloud providers are doing either CDN servers or entire data centers in regions where historically they never would have done it before. Now, let's look at what goes on with cloud networking. Now, before we get too carried away with the networking, we need to talk a bit about how cloud instances are going to work. Most commonly, they'll be virtual machines, which, as I'm sure you're already aware of, are fully virtualized computers, usually servers. Virtual hardware all the way up to the applications and services running on top of them. But we also have the option nowadays of running containers within the cloud, where we only virtualize the software environment in which the app is going to run. And we will also have virtual appliances for the network equipment. Usually it'll be stuff like routers, switches, and firewalls. No, we're not going to virtualize wireless equipment, there's no point. So let's understand the VMs versus the container discussion. Now, if you've already done A+, this should be somewhat familiar to you. A Type 1 hypervisor and a Type 2 hypervisor for virtualization, also referred to as Type 1 virtualization and Type 2 virtualization. Both will have hardware, but with the Type 1, you're going to have the hypervisor running directly on the hardware. Now, once upon a time, these used to be dedicated pieces of equipment that plugged into a computer and took over the operations of the CPU, memory, storage, etc. Nowadays, they're more than likely going to be an operating system that can only run a hypervisor. It can do nothing else. You get things like Windows Server, whatever year, Hyper-V edition. You get KVM Linux. You also get Proxmox. These are all technically Type 1 hypervisors. Whereas with Type 2, you have an ordinary operating system installed on it, and on top of that runs the hypervisor as a software application. Now, with the Type 1 hypervisor, then you get your virtual machines running. You'll have your virtual hardware, a guest operating system, and whatever app or applications you want to run within it. And the same also happens there with the Type 2. Now, the distinction that you are probably noticing is that the Type 2 is going a bit higher, because obviously the host OS needs to take up some resources to run. The hypervisor needs some resources from the hardware to run, meaning there is less available to VMs, meaning this is a more resource-intensive method of doing virtualization. This is more resource efficient. However, it's not necessarily perfect, because this setup can only run VMs. This setup can run VMs when we need it to, and it can be an ordinary computer when we don't. I myself use Type 2 on my computers, so I can run VMs when I need to, and have an ordinary computer environment when I don't. But for a cloud provider, it might be more sensible to do Type 1. Because, well, it's going to run VMs almost all the time, and there'll be very little else you'd ever want to do with that server. But if all you need to do is just run separate instances of applications, virtualization is a very hungry way to do it, whether you're doing Type 1 or Type 2, because you are running multiple operating systems per VM. I mean, for this setup, we've got 3 operating systems, and if they're all the same OS, that's kind of redundant. Same story here. 3 VMs, with 3 guest operating systems and a 4th host operating system. Containerization offers us a lower resource consumption way of doing this. You'll have your hardware, you'll have your host OS, you'll have a container engine, and then the apps run on top of the container engine. The container engine will isolate and virtualize whatever an app needs to run, but that would just be like maybe libraries, DLLs, shared files, stuff like that. Not the entire OS. The app will still rely on the host OS for operating system resources, making this a far more resource efficient way of isolating applications. Now, for an ordinary organization, this could be a great way of running applications that usually don't cooperate with each other when they're installed simultaneously. But for a cloud provider offering something like software as a service, this could be a great way of keeping your tenants' software instances separate from one another without having to go the full virtualization process. Then, for cloud networking, we have something called a virtual private cloud. This is a way of isolating your environment within a public cloud. And what it does is it enables additional layers of security for the customer's virtual instances or applications, or both. And the customers get to set up, configure, and manage their own VPCs. The cloud provider just gives you the compute resources and the capability to put them in VPCs, and off you go. And this is often referred to as cloud within a cloud, although not the best name because it doesn't make it very clear how it works. If anything, it actually is more confusing than helpful. So let's have a diagram to make it easier to understand. So if we have the cloud provider's environment, we have tenant number 1's environment and virtual instances they've paid for. And the tenant can then deploy their instances inside of a virtual private cloud. Consider it a miniature virtual environment in which they run their virtual servers. They can network these guys together and put a firewall between the VPC and the rest of their environment that they have paid for to use in the cloud provider's data center. And then they could also do a second VPC, as long as they've got the compute resources to do this with, and deploy a separate set of servers and have a separate firewall. Now these VPCs could be left isolated, or they could be networked together and provide external access to the customer. Now the cool thing is the customer will connect to the virtual router appliance, and then you might have VPC1 being a low security area that most users can get to, and VPC2 being a very high security area. And this will be as manageable and as effective as formal separation as if you were doing this within your own data center. And this can be done per tenant. So you could have tenant 2 sitting on the same cloud environment doing the same thing, but being kept extra isolated, because the tenant would have to get in from their environment into tenant 1's environment and then into the VPC to possibly mess with anything this customer is doing. And the same would be true of any threat actor as well. Now, let's move on to the connectivity to the cloud. So we get a couple of interesting options nowadays. We get the option to do a virtual private network, or a VPN, which can be very cost effective and easy to implement, and can be pretty well suited when you've got distributed networks, whether it be users all over the show needing to access the central cloud, or a large variety of cloud deployments. You don't have to put all your eggs in one basket. You can use more than one cloud service provider and make them work together. But the downside is VPNs do add a delay to transmissions and communications, so you will increase latency, and this can make bandwidth challenges more significant. Alternatively, you could do direct connect, where you get a lot of good bandwidth and low latency because you do direct connectivity to the cloud. And this is very well suited when you've got very centralized operations where all your users are at one site or one premises, and you just need to sort out direct or high performance connectivity to the cloud provider. But it does require a direct connection to a data center to do this. Whether it be direct physical or direct logical, it needs to be from one site to another. So it does limit where your users can be. Or you can use transit gateways. This is a simplified form of architecture, and it can be used to do multi-VPCs and VPC to premises connections. It does, however, take away control from the customer because the cloud provider operates the transit gateway, not the customer. And it is often web or HTTP driven. Don't worry, you will have HTTPS to help you out with the security side of things. But the transit gateways will definitely be nice because they are an option that will definitely be the whole, you just need a browser to access it kind of gateway. Now, seeing as we had a bit of firewalls, let's talk about cloud firewall security. You can implement the firewall either as a virtual appliance, like I did in that VPC diagram just now, or it could be a host-based firewall in the operating system of one of the virtual machines, just like as if the operating system was running on your own server in your own environment. And this is going to provide you with the ability to segment your VPCs and networking in the cloud and apply filtering between those VPCs based on the functional OSI layer of the virtual cloud firewall that you deploy. If you do it at layer 3, it'll be a basic packet or IP packet filtering firewall, just like in your normal network. We'll dig more into this obviously when we go into the network security videos. You can do stateful inspection at layer 4, where you pay a bit more attention to session information. And you can go all the way up to layer 7, where the firewall is application aware and can make distinctions between what application is busy requesting something through a particular protocol. So we could, for example, prohibit certain browsers being used even. Now, in terms of implementing a cloud-based firewall solution, there are a few things to consider. So as we've already said, you can do it as a host-based firewall on your virtual machines, or you can do it as a virtual appliance at the VPC level. But the things you need to factor in here is you are running an extra compute resource in the cloud, which means it will consume more CPU resources, driving up your cloud costs every month. And it is going to add additional management complexity because obviously you've got to administrate this thing and configure it. The cloud provider is responsible for making sure it is able to run, but you are responsible for setting up the rules and the access control and all of the security of it. But the benefits are you're going to have a very scalable and flexible firewall solution because it's running in the cloud, and it will help a lot when it comes to data protection law compliance, as a lot of the legal requirements might stipulate the need for a firewall to protect certain systems. But we have other options when it comes to the cloud. We can do, for example, a cloud security group. This can act as a virtual firewall for instances to control inbound and outbound traffic, and it can run with far less resources than a cloud firewall does. Its functionality is going to be able to operate on an instance level, and it'll be able to do stateful filtering. So in other words, it's going to work like the layer 4 firewall, and will allow you to specify rules, and all unmatched traffic is dropped. Pretty simple and pretty straightforward. But the thing is, it works on a group level of instances and users. It doesn't give you a fine-grained level of control. But we also have something else. We've got cloud security lists. This will operate at a subnet level rather than an instance level. So it's going to be like your VPCs, for instance. Although you could actually do even further segmentation if you do a virtual router instance in a VPC that would give you the ability to have more subnets per VPC. And this runs with, again, less resources than a cloud firewall does, but it offers stateless filtering, very similar to a layer 3 firewall. And you can set allow and deny rules to finally control the traffic flow, very similar to using an access control list. And this is quite nice to apply broad network policies that are uniformly applied to all instances within a network. So you don't have to just go for the cloud firewall option. In fact, it might be better to use groups instead of a layer 4 firewall and security lists instead of a layer 3 firewall, meaning that you'd rather keep the more resource hungry type of firewall for layer 7 when you want to do the application level traffic filtering. But cloud computing is not a one-way thing. It's not just about our networks getting us to the cloud. Cloud has been coming into our networks, and we're sort of calling this the cloudification of our networks, where we've been getting a bit of cloud technology coming in and innovating and improving on how our network infrastructure is going to be facilitated and managed, for better or for worse. One of those things is something called infrastructure as code, or IAC. Now this is where your infrastructure management for both networking and services is going to get managed via software coding, basically software development almost. Now this is going to be quite cool because it's going to make it very easy to do scripting and automation. And because of scripting and automation, you could also make it very easy to do rapid deployments of new infrastructure and services. Again, because of the automation and the scripting benefit, you'll also have very consistent deployments of your things because you developed either a script or a bit of source code that goes and does all the work for you. But to me, one of the biggest advantages of infrastructure as code is we can take advantage of software version controlling and collaboration to make it a lot easier to do configuration management. One of the biggest pain points that you'll come across with network documentation is very, very bad change tracking. But because you're going to be using software development practices, you could literally track network changes using Git, which is freaking amazing actually. Now, popular tools, at least according to CompTIA, to do infrastructure as code are Terraform, Ansible, Chef, Puppet, and AWS CloudFormation. Please be aware, these are popular tools according to CompTIA. I do not necessarily recommend or discourage the use of any of these tools. I'd rather you do your own investigation and homework and decide which one might be right for you in your workplace. And that is assuming that even infrastructure as code is right for you in your workplace. Just because it's new and innovative doesn't mean you need to jump on board straight away. Another thing we also have is something called Secure Access Service Edge, or SASE. This is a cloud-based architecture where we combine network and security functionality for widespread global reach. The idea is at your perimeter of your network, you're going to have a little bit more cloud integration, a little bit more cloud services to manage both easy access while maintaining security. What's pretty cool about SASE is it is going to integrate very well with SD-WAN technology and something we're going to talk about now called Secure Service Edge. The big advantages obviously are simplifying your WAN architecture because of the SD-WAN aspect, making your security posture a bit better when it comes to access in the cloud, and hopefully reducing overall complexity and processing overhead, while also making the user experience better by making the security less annoying and obstructive. And as I said, this does work with Secure Service Edge, or SSE, where we use this to manage and enforce security policies, look for malware, monitor and audit our network activity, and mitigate data exfiltration methods. Now, by doing this effectively in our perimeter network, we can make sure that the cloud does not become too much of a security liability to our operational network security. Usually this is best done with a cloud access security broker, or a CASB, an organization you consult with to help facilitate more secure connectivity with your cloud instances. Yes, we are introducing a middleman, but CASBs usually specialize in making sure that customer-to-cloud connectivity is done as reliably and securely as possible. And then we have SDN and SD-WAN, bringing virtualization and a bit of cloudification into our networking. Now, SDN is usually applied within a tenant's VPC infrastructure or within your own local network at your offices to manage the LAN aspects of network communications. And SD-WAN can do a lot to help manage the customer's connectivity to their cloud service provider more effectively. I would suggest you go back and check out my Module 22 video on SDN and SD-WAN if you want to learn more about this. I covered it in greater detail there already. Now, there are a few data center design principles I'd like to introduce you to. Whether you are looking at working at a cloud provider or you're looking at just improving your existing data center to make it more competitive with a cloud provider's data center, let's look at some design principles. One of which is adopting a spine and leaf topology. This is a two-layer network design, utilizing switches to try and optimize how traffic flows through your data center. The spine layer of your network is meant to be the backbone, or top tier of distribution switches that will interconnect with all of your leaf switches, but not with each other. So it'll go from network core to the leaf layer, but spine will not connect to spine. And the leaf layer is there to provide access to the actual servers that are going to be connected to this network. And they're going to go full mesh to the spine layer. And they'll facilitate direct connectivity from devices to network backbone without any sort of interleaf connectivity. Let's have a diagram to make this more sensible. So let's have a little zone for our spine and stick some switches there. Let's put the leaf layer in and stick some switches there. And this is how we interconnect. You can see how the spine switches don't connect to each other and the leaf switches don't connect to each other. But leaf to spine full meshes. So if something goes wrong with that spine switch, we can get to that one. If we need to talk to somebody connected to that leaf switch, we can go there to there or there to there. We've got choices. And what happens is the leaf switches connect to the server racks. Oftentimes the leaf switch is going to be your top of rack switch, positioned at the top, providing connectivity to all of the servers in the server cabinet. And then your spine layer is meant to connect to your network core. And you can egress to the rest of the network either via a layer 3 switch or via a router, entirely your choice. But this is your spine and leaf topology. Now, a term that you want to get used to when dealing with data center networking is north and south traffic. North and south traffic usually describes traffic leaving or coming in to your data center. But you also get east-west traffic, which describes traffic going from one server to another within the data center. Now, the big advantage of going for the switch-based approach here is switches do usually offer us way faster transmission time and much lower latency. So pretty cool. But layer 3 switches do give us the opportunity to start doing a bit of layer 3 filtering as well. So we're getting a bit of the best of both here. So let's run through some of the benefits. Because of the switch design, we get very, very predictable latency. If we had the leaves interconnecting and the spines interconnecting, things like spanning tree protocol and all of its variants could come along and mess with us. We're also getting some very good load balancing and failover capabilities with the redundant path in and out of the data center. And it is naturally a loop-free design, so you could even consider disabling spanning tree protocol. Personally, I wouldn't. I kind of like having it. It's not like it's going to keep changing everything up every 5 minutes, but some organizations prefer eliminating that potential delay in communications in the data center due to SDP or even RSTP wanting to reconverge. If you want to see more, please feel free to go back and check out my SDP video. It'll probably clear up a lot about how SDP performance affects networking. But it's also a very scalable and redundant network design. If I need to add more leaf switches, I just need to make sure that they have redundant connectivity to the spine. If the spine starts running out of capacity, I just add another spine switch. And it effectively gives us high-speed connectivity. Another thing that you'll find in high-performance data centers are storage area networks, or SANs. Now, SANs are a very specialized kind of network storage dedicated to providing block-level access to the storage. Now, that's actually very special because things like NAS appliances, file share servers, and so forth, they don't provide block-level storage. They provide file-level storage, meaning you can see the data files, but you don't see the underlying blocks of storage. Now, SANs do utilize very specialized appliances, storage devices, and network media, as well as network standards and protocols. This means that network administrators are generally not expected to become SAN admins as well, but a bit of familiarity with how SANs work would be expected out of a network administrator. So let's try and see what goes on with SAN infrastructure. So first, let's have a server with some normal network connectivity. And to get the server communicating on a SAN, it gets a SAN HBA, or host bus adapter. Now, the sharp amongst you will remember that the term host bus adapter usually applies to the thing that connects motherboard to storage drives like HDDs and SSDs. Yet we're talking about this for a network connection, and yes, you're right. It's sort of like a network card, but it's treated as a disk controller card as well, because it's going to provide connectivity to the SAN, which is going to be seen by most computers as just this big block of storage that just happens to use networking to access the actual data on the disks. Now we're going to use fiber channel cables for a proper true SAN. These are fiber optic cables, but it's a special kind, designed and dedicated for storage area networking and carrying particular protocols and layer 2 standards. These fiber channel cables will plug into specialized switches called fiber channel switches. And we will use the fiber channel protocol to transmit storage instructions. Now you'll probably notice the spelling is a bit different to how I spelled fiber in the network media chapter. And that is because we usually use the British spelling for fiber channel to distinguish it from fiber LAN and WAN cables for ordinary networking. It's a small distinction, but worth noticing. Most people don't know it, but hey, now you do. Now, all well and good, we've got this very cool, fancy, dedicated network media, dedicated switches, but how does the storage actually happen? Well, we get these appliances called storage controllers. They're sort of like a network attached storage or a NAS device with disks connected to them, but they're a bit more sophisticated and work specifically with fiber channel. And what will happen is they'll be connected to storage units, highly specialized disks that get connected to the storage controllers. In some cases, these storage units can even be connected to multiple storage controllers for absolute redundancy in pathway from the server all the way to the storage unit. Being a network, we need a way to address and communicate with the storage units. But being a very different kind of protocol, obviously we're not going to use IP addresses. What happens is these disks are addressed with something called a logical unit number. It's sort of like an IP address in that it is a logical addressing system, but it is going to be used to identify both the storage unit and the block of storage that you need to access, which is pretty damn cool. And what will normally happen with most fiber channel protocol implementations is they usually carry SCSI storage operations. SCSI being the Small Computer Systems Interface that was a very popular disk connectivity standard many years ago when computers were still beige. And funnily enough, SCSI commands are still quite commonly in use with most SATA disks and something called serially attached SCSI, which is a type of SCSI disk that uses a SATA connection. Very popular on servers actually. So although the physical SCSI standard has died away long ago, and most of you probably haven't even heard of it or seen it, we still use their commands to this day for a lot of storage operations. Now, one problem with SAN infrastructure like this is very specialized and very expensive to implement. And a lot of organizations might want the benefits of a SAN, but can't easily justify the expense of this kind of infrastructure. So thankfully, we've got other ways of doing SAN infrastructure. I could decrease the SAN a little bit by having just my storage units and storage controllers and my server and the normal network over there. And then to get from the server to the SAN, I can deploy an ordinary network. Ordinary Ethernet cables, whether it be twisted pair or fiber, doesn't matter. Ordinary switches, Okay, that's interesting. And I will then use FCOE, Fiber Channel over Ethernet, where the server will take its Fiber Channel Protocol message, and instead of putting it into an FCP packet, it will encapsulate it in an Ethernet frame, send it through the network, and it'll get to a storage controller that will have to have an Ethernet interface as well as obviously Fiber Channel interfaces. And the storage controller will understand both TCP/IP and Ethernet, as well as FCP to communicate with the storage units. Okay, cool, nice option. So you can use normal network infrastructure to get quite close to the storage units or the disks. But we can take it a few steps further. That server that gets connectivity to the SAN, whether it be through Fiber Channel Protocol and a SAN HBA, or through FCOE, doesn't matter, we can treat that server as a SAN gateway. And the rest of the machines in our network that need to access the SAN can do so using IP communications. Get it to that server, and that server acts as a bridging gateway, converting ordinary IP communications into whatever is necessary to communicate with the actual storage units in the SAN. Now, because we're using routing and IP networking, what we'd probably use is something called iSCSI. SCSI commands that get stuck into an IP packet and get sent to a server acting as a SAN gateway. Pretty cool. And iSCSI will recognize the LUN numbers being used in the SAN to address the storage units. So we get the best of everything here. There are choices when deploying with a SAN. It's one of the reasons why a lot of bigger organizations like them. High speed, high performance, and highly flexible if you have a specialist that knows what they're doing and works well with the networking admins. And networking admins who also know a little bit about how SANs work. Let's talk about how they get used. Normally, organizations like to use a SAN when we need very high available network storage, and we need a very scalable storage solution that has very low latency when accessing it, because nowadays we're starting to realize how big an issue latency is in the network when it comes to accessing storage. You can have the fastest process, you can have the fastest disk, but if your network can't keep up with getting the data from the disk to whatever's going to process it, you're going to have computational delay. And one of the real big advantages is you get block level access to the storage. So whatever works with the SAN, it can treat those SAN disks as though they were directly attached storage. It is as though the operating system can reach out and touch the disk directly and not really have to go through a network. As I said earlier, NAS appliances and file share servers share just the file. When you connect to them, you see the file, but you don't see how the file is stored. You've got no way of controlling, managing, or optimizing that. So some common use cases for SANs are high-performance databases, storage for large, high-performance data centers, and obviously cloud data centers. Now, if you feel a bit intimidated by the SANs, please don't, because Network Plus is not expecting you to be a SAN expert, but some familiarity is quite useful. And for some networking professionals, the idea of this kind of interesting storage network is massively appealing. But that is all you need to know about for the basics of cloud for Network Plus. Obviously, as I said earlier, there are a couple of cloud courses from CompTIA that you can check out. And you can also go and check out the cloud vendor's own courses as well if you want to learn more, which I highly encourage you to do. Otherwise though, I'd like to say thank you for watching. I really appreciate it. If you have any friends, family members, colleagues or peers who would also like to learn Network Plus, don't be afraid to share this video with them. Otherwise though, I'll catch you in the next video.